What? All right, we're on the check your understanding. Does fidgeting keep you slim? Some people don't gain weight even when they overeat. Perhaps fidgeting and other non-exercise activity or NEA explain why. Some people may spontaneously increase non-exercise activity when fed more. Researchers deliberately overfed a random sample of 16 healthy young adults for 8 weeks. They measured fat gain in kilograms as the response variable and change in energy use in calories from activity other than deliberate exercise, fidgeting, daily living, and the like as the explanatory variable. Here are the data. So this is data that you would put in L1 and L2. Your NEA change would be in L1 and your fat gain would be in L2. I do not want you to put it in yet though. We're gonna talk about all of this. It gives you your regression and this is your regular plot and then your residual plot. So then you have your regression analysis and think about where those numbers go in the formula. So construct and interpret a 95% confidence interval for the slope of the population of the true regression line. So the first thing that we're going to do, of course, is state and what goes in our state. Give me 2 seconds. Sorry, trying to figure out the afternoon. All right, say it again. So 95% confidence interval in context of the problem. And it's the slope of the population regression line relating fat gain to change in NEA. Everybody good? All right. So then what are we going to do in the plan part? What test are we doing? It's not necessarily a test, but what letter? Oh, no. What are we doing? It's a letter.
We're doing a linear regression.
A T. Okay, we'll start there. It's a T, not test, but a T what? Interval. And it's for slope. And yes, now you do check the conditions. Okay. So L is for linear. 2 things, either one, it doesn't matter. So the scatter plot, that's this one. Shows a really linear relationship. Or you can do the residual. Shows no pattern. What do we do for the I? Why? Why?
Because if it's less than 10% of the population, then it works.
We are sampling what?
Oh,
without replacement. So if we're replacing them, we don't have to do the 10%. Realize that. Okay. So if you replace them, you don't have to. You could just say sampling with replacement, check it, move on. Okay. So this one was without replacement. The N. Normal. What I didn't do, and I apologize, is I did not put, because it was on the opposite page and I didn't even look at it, put the histogram on here. Again, if we're putting this into stat, we have the data. What would I make? Would I make a histogram? What would I make? No, I would not.
Box
A box plot. I would make the box plot because it's easier to see the outliers and the normality in it. Okay, so if they give it to you, just draw the box plot there. So you would draw your little box plot or whatever. And you would see no strong skew or outliers. The histogram shows no strong skew or outliers, and it's on page 5. It's 753, but you don't have to look at it. I'm just telling you, if you were doing this 2 different ways, if they don't give you the histogram, do the box plot. It's so much easier to do that. All right. E
equals
equal SD. So it's roughly equal scatter for all X values. And then the last one is the R. And we took a random sample of 16. Is everybody good? Remember, if you do an experiment, it'll be random assignment. Okay, it'll be random assignment that you're looking for. All right, so in the do section, to figure out your interval based on all of your stuff right here, you're gonna use your formula or whatever. So the first number in your formula is gonna be this one. Remember, we do, they do A plus BX, sorry. They do A plus BX, so your coefficient or your number, your constant comes first. So that's what this number is, it's your constant of coefficient. So negative 0.00344415. And all Minitab outputs pretty much look like this. They're not going to switch it around. So know that the first number is the first one. I got that? So plus or minus. What am I doing? Plus or minus. We have to figure out our T star. How do we figure out our T star? We want 95% confidence. So what's our area for this? 0.25 degrees of freedom.
14.
Why is it 14?
We do -2.
-2. So anytime we're doing slope, linear regression is always -2. Everything else is -1. Okay, so linear regression is -2. So when we do this in our calculator, our T star is going to be 2.145. And then we're going to multiply it by your standard error, which is this one right here, 0.000714. Again, I'm going to show you how to do this in your calculator. Right now, we still don't know how to do that, so that's why I'm showing you by hand. Okay. Sorry. Our interval, when we put it in our calculator, is negative 0.005032 to negative 0.001852. And then our conclude, we are 95% confident that the interval, and you're going to make sure that you write that interval down, captures the slope of the population regression line sorry, I'm running out of room, relating fat gain to change in NEA. Gosh, check your cells on these to make sure that you did it right. And the one way that you can do that is look at our interval. What kind of numbers do I have in my interval? Negative. What was this relationship? Negative. If you came up with positive, you know you did something wrong. Okay, so make sure you check that. Any questions?
Can we say capturing the slope, or does it have to say capturing the true slope? Well, I know that was the thing with the mean and the portion.
You can say the slope because it's the population regression line. So as long as you put that in there. If you say the true slope, you don't have to put the population part in there. Got it? Is everybody good? All right, so in your calculator, sorry. Football is still playing. We're not cheering. Okay. That's what all this is about. So I apologize, y'all. Oh, sorry. Put this in your calculator. Go ahead and put these values, L1 and L2. So go ahead. You're just defining, oh Lord, sorry. Emily, for the full state part, you're just defining what's your beta, like your confidence interval, 95% confidence interval for the slope of the population or the true population regression line. That's it. Y'all, if you chat, I don't see it pop up. So it's best if you just interrupt me. Okay. Put these numbers in. If you don't have a calculator, put them in. I'm about to be mad at you. Say it again.
Is L1 in the ocean?
Yes.
Is there supposed to be something after the 10 point?
Oh, it's not a 10. I'm glad you pointed that out. It's 1.0. Thank you. All right, so you have your L1 and L2 in. You're going to go back to stat. You're going to go to tests, and it's easier if you just go up. One of them is the t-test, and one of them is the interval. We want the interval because that's what we're doing right now. When you hit enter, it asks about L1, L2. Make sure your confidence level is at a 95. And then you calculate.
This frequency?
It's just one. Yep. That's it. Is that good? Notice your R down here. That is your correlation coefficient. So it is a negative, and because it's 0.7, it's strong. Okay. So you talked about that like in math 1. If it's negative and it's the closer it is to -1 or +1, the stronger it is. The closer to 0, it's super weak. Got it? So just wanted to show you that real fast. All right. So same thing. You can do them all that way. I don't care. All right. T-test for the slope. So that was interval. I told you where the test was. You'll do that as well. To test the hypothesis, H sub O, beta equals beta sub 0. Compute the test statistic. So T equals B minus beta sub 0 over the standard error of data, or B. Your stuff tomorrow is in Albert. I have done all the problems. They are not hard if you will look at your notes. Does everybody understand that? I looked at every single problem. I did every single problem. If you look at your notes, you will be fine, okay? I think there might be one that deals with this formula right here, and that's it. And it's like you plug in the other values to solve. It'll give you like T is blah, blah, blah. What is B? And it'll give you the other two as well, okay? So just letting you know that that might be in there. The probability of getting a T statistic this large or larger in the direction specified by the alternative hypothesis. H sub A. Use the T distribution with degrees of freedom equal to n minus 2, and we got a little bit to draw here. If our alternative is that beta is greater than the hypothesized value, again, typically 0, but it could be more, then our T is going to be here and everything will be to the right, greater. If we have beta less than the hypothesized value, it'll be on this side. And then the last one, if beta does not equal the hypothesized value, remember not equal is two-sided. All right, flip it over. Infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. Child development researchers explored the relationship between the crying of infants 4 to 10 days old and their later IQ test scores. A snap of a rubber band on the sole of the foot caused the infants to cry. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later measured the children's IQ at age 3 years using the standard Binet IQ test. The table below contains data from a random sample of 38 infants. I would never want you to put all this in, okay? So we're gonna do this one by hand because it's gonna be easier, all right? So some computer output from the least squares regression analysis on these data are below. So there's your Minitab, there's your regular scatter plot, all right? And flip it over. There's your residual and then your normal probability plot, okay? And remember, we want that normal probability plot to be linear. Okay, so it looks pretty good. So A says, what's the equation of the least squares regression line for predicting IQ at age 3 from the number of crying peaks or cry counts? Interpret the slope and the y-intercept of the regression line. This is the worst one, okay? So you can write it y equals a plus bx if you want to, but then you have to define what y and x are. Y'all understand what I'm saying? If you'll go ahead and put in what it stands for, then you don't have to define it later on. I think we've talked about this before in previous chapters, okay? So what we're looking for is a predicted IQ score. All right, we are not working with the T interval right now, okay? We're just working with the equation. So remember your Minitab output for the equation, when you go back, your constant of coefficient is this one. This is like your y-intercept. Okay, so you know what it is. It's your y-intercept. Again, this is different from the interval that we just picked up stuff. everybody good? All right, so we start that equation, 91.268. We're going to go back to the other side. And this number is your slope. And we already knew that because when we do our interval, our slope comes first. Slope plus or minus the t star and then the standard error. Got it? Is everybody good? All right. So the slope is 1.4929. And then our X value, if you guys look over here, our X value are cry counts. So that is your equation. Now, like I said, you can do it y equals 91.268 plus 1.4929x, but then you have to define what x and y are. So it's a little bit easier. Just go ahead and put it in there. All right. So then we need to tell what the slope is. We need to interpret the slope and the y-intercept. So for the slope, it's just like back in the day, math 1. For each additional cry peak, you could have said cry count, okay, because that's what they were measuring. In the most active 20 seconds, this is just context of the problem. The regression line predicts an increase of 1.4929 IQ points. The only thing that may change, so this is context of the problem. It could be decrease. So if you got a negative slope, it's going to be decrease. And then whatever the number is and by how much, or in context of the problem. Okay. So then your y-intercept. Remember, your y-intercept is where you start. It's when x is 0. So that's what we're going to talk about right here. The model predicts that an infant who doesn't cry when flicked so 0 cries, remember x is your cry, so when x is 0, with a rubber band, we'll have a later IQ score of about 91. That's this number right here. And again, a later IQ score is context of the problem. All right. B says, explain what the value of A means in this setting. So A is that AX plus B, this one. So it is the size of a typical prediction error when using the regression line in part A is 17.50 IQ points.
What did you get that number?
When you flip it over, I don't think it's supposed to say F's. I think it's supposed to, I think it's supposed to say F and not A. Change it to F's. That's your standard deviation. In a minute. Is everybody good with that F? All right. No worries. C, says, do these data provide convincing evidence of a positive linear relationship between crying counts and IQ on the population of infants? So how do we figure that out?
The-
If we're doing convincing evidence, what do we got to do? How do we start? State, plan, do, conclude. What's your state? So we haven't really set any hypothesis yet, so I'm going to show you how to do that right now. So our null hypothesis, we're talking about slope, and remember that's beta. If it equals 0, there's no relationship. Okay, there's no relationship. It's just a flat line. Okay, your slope is 0. All right. So then your alternative. What did it ask us to do? What kind of linear relationship? So what kind of numbers do we have to have? Greater than 0. Very good. And then also in here, you want to define what beta is, the slope of the regression line, relating cry counts to IQ, later IQ. You got it? So define what beta is. Same thing we've been doing. And then the other thing is, and what's our alpha level? Yeah, it didn't say, so we're going to do 0.05. Plan. You're going to do the liner. We're not going to write all this down just to save a little bit of time, but is it linear? For what 2 reasons? Scatter plot shows no pattern. No, scatter plot shows what? A linear pattern. What shows no pattern? Residual. Make sure you don't mess that up because I mark it wrong. Okay. All right. So what about I, independent? We're picking out babies. Are we putting them back? No. So what do we have to do? The 10% rule. So 10 times 38, and there's definitely more than 380 babies. What about N? And there are a couple different ways that you can do normal. This one didn't give you a histogram either. I didn't want you to put all those values in. You can. But what you can look at on this one, and you can make this note yourself because I'm not writing it down. The normal probability plot is linear and has no skew. So there's no curve in there. Okay. So normal probability plot shows no skew. Right. What about E?
The residual plot
Is scattered around 0, equal scatter. And then R, we picked a random sample of 38 infants, so all of it passes. And our do, they give you your T value and your P value, okay? So if we flip back, here's your T value. This is actually your P value, but you need to be careful because it is two-sided. Because your chart is not equal to, okay? It doesn't specify a side. So think about that for a minute. This is a two-sided p-value. And then, how many babies did we have? 38. Okay. So your T was 3.07. Your number of babies was what again? 38. So what are your degrees of freedom? And then your p-value, it said was 0.004, but it's two-sided and I need one-sided. So how do I do that? Divide by 2, which equals 0.002. You don't have to do any work. It's got all of it for you. There's no intervals, anything crazy that you have to do. There's no putting it into your calculator. It shows you everything in the chart, okay? And then conclude. The way we conclude is your p-value versus your alpha. Our p-value is 0.002, which is less than 0.05. So we reject H sub O. And then I am going to write the full statement. There is convincing evidence of a positive. Where did that come from? That was the alternative hypothesis. Remember, everything's based off that. There is convincing evidence of a positive linear relationship between intensity of crying and IQ score. You can put later IQ score, it's fine, in the population of infants. And then the next two are very short. The next two are very short. So if you're going to do this in your calculator, you go to the same place to do the test rather than the interval. So on this technology corner, to do a significance test for slope, you're going to go to stat, test, and a LinReg test. Yes.
For the plan on the previous one, what would you put that you were doing, when you were writing to these guys?
We were making a t-test, yeah, for slope. All right, that's it on that page. And then the last thing is just check your understanding. And again, everything is within that chart, so there's no real work to do. It's going to be really quick, okay? The other thing that makes it really quick is it says, assume that the conditions for regression and inference are already met. So we don't even have to do the liner stuff because they already told us, okay? So what is our state? Our problem says the previous check your understanding, the one that we just did on NEA and fat gain. Here again is the Minitab output. Do these data provide convincing evidence at the alpha equals 0.05 significance level of a negative linear relationship? A negative linear relationship between fat, I should say gain. Wow, y'all should be used to it by now. And NEA change in the population of healthy young adults. Assume that the conditions for regression inference are met. So what is our state? And your first one is? And your alternative is? Very good. And then your alpha is? And then make sure, good gracious, you define what beta is. It is the slope of the true population regression line. Relating blah, 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 blah. Okay. We are going to do a t-test for slope. And conditions are met, so we can move on. Oh, don't want to move it too far. We need three things: your T, your P, and your degrees of freedom. So what is your T value in this one?
Maybe 4.60.
What's your degrees of freedom?
Whatever it was, I don't remember what it was.
There were 16 people.
So 14.
And then what's your P value?
Yeah.
And again, it's two-sided in the chart, so we're going to divide it by 2, which is still going to give you, it doesn't matter, it's still going to give you 0. Okay, it's way too small. So it's approximately 0. Conclude, we're going to test our P value against our alpha, so 0 against 0.05. Your P value is less than alpha, so we reject H sub O. There is convincing evidence of a negative linear relationship between the fat gain and any change in the population of healthy young adults. Again, your stuff is all stated within your problem. It just sucks that you have to keep writing it down. Okay. Everybody good? All right. So we're going to stop there. You guys are going to finish your alternate examples today.